It's a little laser unit, roughly maybe half that size, but it only requires a watt to shoot a stream of photons through here. Just imagine a little hole, where a fiber optics cable could go through here. Then you have a diffracting lens that would spread the stream of photons from this all the way to this diameter. So it just expands it out to here. These are roughly a bundle of 500 YBCO superconductor coated quartz tubes. If you were to draw just a line with a pen or a pencil on your paper about an inch long, that's the size of one of these little tubes. So you just get a big bundle of these. Superconductors, YBCOs require liquid nitrogen to operate as a superconductor. So this entire unit would be at liquid nitrogen temperatures.
The small little piece in between the quartz tube and the magnet, what is that again?
Just a diffracted.
Does it expand? Okay.
Okay. We'll cover the two paths. You've got, we'll just call this path A. It would be right here for the magnetic flux coming out of the magnet, returning. It does that automatically. When you cool this device to superconducting temperatures for YBCO, these little tubes create vortices that decrease the permeability, which turns this from an insulator into virtually a perfect conductor of magnetic flux. So once this is cooled to liquid nitrogen temperatures, it automatically defaults to this path, path B. Now the only way to get it back to path A is either increase this above liquid nitrogen temperatures, or so that YBCO is no longer a superconductor, or here's the trick, and you'll hear the word resonance again. That's where this one comes in. At roughly 930 nanometers, YBCO.
What does that measure? Nanometers? Wavelength?
Yeah. From 0, just say 1,000. Doesn't matter. Beyond that, it's not absorbing at all. This is roughly what it looks like, and then it peaks right here, around 930 nanometers. It's just happens to want photons from a laser unit at that specific wavelength in order to disrupt the superconductive state. Now, if you were to just follow one photon as it's going through here, as soon as it hits the YBCO material, it initiates an avalanche effect. At this wavelength, it'll absorb the photon, and then Cooper pairs that create these little vortices are disrupted. And one photon can disrupt up to 340 theoretically. And what that will do is just disrupt the flow of electrons through these tubes sufficiently such that the photon no longer sees this as a perfect conductor of magnetic flux, or the magnet rather, so that it just reverts back to path A. So that's how you would change paths. And now here you have copper windings, and when you change the amount of magnetic flux flowing through copper windings, it produces electricity. It's doing that in my Toyota Prius as I'm driving down the road, so it's nothing new. I mean, that's just standard magnetics. But this resonance effect plus the avalanche effect allows you to change paths. And the only input is this right here. So to reset this, here's the weird thing. And again, superconductors have some weird properties, but this one, in this particular configuration, combines all these properties into a manner that will allow this to happen. As soon as you shut off the flow of photons, YBCO says, well, okay, I can just go back to the way I was. And it prefers its original configuration. So the Cooper pairs, these are electrons that basically just travel together in pairs. Once again, creates these little vortices so that the magnetic flux wants to go through this path instead. And you didn't put in any energy to do that. turned off the laser unit. So if you turn it back on again, follow a photon through, avalanche effect, disrupts the flow of magnetic flux, and then it goes here again. Turn it off, and it goes around here. And that's about as simple an explanation as I can get with this. But again, when you're involving superconductivity, and if you pick up a book on superconductivity, they have equations, like half a page, one equation. It's the sort of thing I don't want to go near, but I have to talk about it, so there's that. But it also involves vortex physics, and there may be a dozen people that have a thorough understanding of that. Then you have electromagnetics, you have to deal with that, plus a ferromagnetic core that follows a hysteresis curve. As far as the energy, when you're shifting magnetic flux from one path to another, it doesn't just go on, off, and here. It follows a curve. Instead of a straight line, or actually a square curve, on, off, on, off, on. It follows a curve. It's a gradual change. So the frequency is what dictates how often you change paths, the on-off in the laser unit. The higher the frequency, the more energy you produce, more electricity that can power whatever you want. The material constraints are dictated by a hysteresis curve, as well as the AC losses in the copper windings. So theoretically, the limit of a device like this would be roughly 100 kilohertz, and 65 is 11. That's about 20 kilowatts for this device. So to just put in an estimated efficiency, roughly half that. So we refer to this particular device as a 10 kilowatt prototype.
Then it stays in one band?
Yeah, you have to. When you change magnetic flux, the amount of magnetic flux over a given period of time through copper or even superconductor windings. I mean, in this case, you could use superconductor because this whole unit would be cooled to that temperature, which means it would increase the efficiency even more. But every time you change the path is proportional to the amount of electricity generated. That's why you want to increase the number of times you change that path, or you increase the frequency of the on-off switch here with the laser unit.